Representation Theory of Finite Groups, Lecture 22, Jeu de taquin. Let us start with motivation. Recall that we have a Robinson-Schensted correspondence, which is a bijection between the set of all permutations of n elements and the disjoint union over all partitions lambda of n of the Cartesian product of the set of standard Young tableaux of shape lambda with itself. Recall also that for any permutation in Sn, let's denote this permutation by sigma, it sends 1 to A1, 2 to A2, and so on, n to An. We have defined the reversed permutation sigma r, which sends 1 to An, 2 to An minus 1, and so on, n to A1. So this reversed permutation is obtained from sigma simply by flipping the second row. So assume that the Robinson-Schensted correspondent of sigma is the pair consisting of the insertion tableau P of sigma and the recording tableau Q of sigma. Then we have already seen that the insertion tableau, which corresponds to the reversed permutation sigma r, is obtained from the insertion tableau of sigma by transposition. This is P of sigma transposed, and T denotes the transposition. So the question which we would like to answer today is how to determine the recording tableau which corresponds to the reverse permutation sigma r. So for this, we would need to talk about skew diagrams and skew tableaus. Let lambda and mu be two Young diagrams of possibly different size. Assume that mu is contained in lambda in the sense that each mu I is less than or equal to lambda I. Definition: the skew diagram lambda modulo mu is defined as a collection of all boxes of lambda that do not belong to mu. Here is an example. So assume that lambda is the partition 4, 3, 3, 2, 1, and mu is a partition 2, 2, 1. Then lambda over mu is the following skew diagram. So it has two boxes in the first row, but they start from the third position. It has one box in the second row, which starts from the third position. It has two boxes in the third row, which start from the second position. And then it has two boxes in the fourth row, which start from the usual first position, and one box in the fifth row, which also starts from the usual first position. And similarly, one defines the notions of skew generalized Young tableaus. So if mu is the empty tableau, then we recover the usual notions of Young diagrams and Young tableaus. So here are some examples of skew generalized Young tableaus. So the first example is simply we filled in the boxes in the previous example by some numbers, and we did it so that they increase left to right and top to column in all rows and columns. And here are some further examples which can be easily seen are obtained by taking a Young diagram, taking away some its Young subdiagram, and then filling in the remaining boxes with some numbers. So now we are going to define some procedures how to manipulate skew Young diagrams and tableaus. And the first part of this procedure is the so-called elementary move forward. So the input for this elementary move forward is a skew Young tableau, which has the following local fragment. So we have this kind of picture when we have here an empty box, which we marked by the magenta color. And to the right of it, we have a box with a number A, and below it, we have a box with a number B. So in the general case, one of these boxes might be empty again. And we call the magenta box the active box. So it should be empty, so it should not contain any number. But this box is distinguished as a box which we call active. Another important input condition is that the numbers A and B should be different. So what is the output of the elementary move forward? We will have to distinguish two cases. Case 1 is when A is smaller than B, or B doesn't exist. So the box containing B is actually empty. Then the local picture will be changed to the following picture. So we swap the box A and the active magenta box. Case 2, this is when B is smaller than A or A is an empty box. Then the local picture changes to this picture. In other words, we swap the active box and the box B. So here are some examples. So if we have the active box with 2 to the right and 3 below, so this is changed to the picture when we have 2 instead of the active box. The active box moves to the right and 3 remains below. And if you have a picture, the active box 4 to the right and 3 below, then we swap the active box and 3, because 3 is smaller than 4. And the two main points to notice here is that, first of all, in this local picture, the outcome is locally standard. So in this picture, 3 and 4, they increase left to right, and here 2 and 3 increase top to bottom. And also that the active box moves. So the active box moves either to the right or downwards. So now with this elementary move forward, we can define the forward slide. So the input of the forward slide is a skewed generalized Young tableau with different entries of shape lambda modulo mu and a fixed removable node of mu. So how do we do the forward slide? We declare our fixed removable node of mu active. And while the active node is not a removable node of lambda, we perform the elementary forward move with respect to this node. An output will be a new skewed generalized Young tableau of some shape lambda prime modulo mu prime, where mu prime is obtained from mu by removing the originally fixed removable node, and lambda prime is obtained from lambda by removing the active node at which the algorithm terminated. So here is an example. So assume that we have this input tableau. It is of the shape 5, 5, 3 modulo 3, 1. So in the first line we have 3, 4, in the second line 1, 2, 5, 6, and in the third line we have 7, 8, 9. And we declare the removable box in the first line for the 3, 1 active. So let us do the forward slide for this box. So we start with our tableau and this active box. And we see that to the right we have 3 and below we have 2. So we should replace the active box by 2. So we swap the active box and 2 and we have this picture. The new active box has 5 on the right and 9 below. So 5 is smaller, so we should swap this box with 5. And now we have the active box with 6 on the right and nothing below, so we just swapped it with 6. And finally we get a situation where the active box is a removable box of the original Young diagram. So therefore, at this stage, the algorithm terminates, and our outcome is a skew tableau of shape 5, 4, 3 modulo 2, 1, and the numbers 2, 3, 4 in the first row, 1, 5, 6 in the second row, and 7, 8, 9 in the third row. Let us now define the inverse procedure, an elementary move backward. So the input for this is the following local picture. So we have an active box colored by magenta, a box with A above it, and a box with B to the left of it. And it is possible that one of those boxes doesn't exist. And the important assumption that A and B are two different numbers. The output, again, two cases. If A is smaller than B, or A doesn't exist, we swap the active box with B. Case 2, if B is smaller than A or B doesn't exist, then we swap the active box with A. So here are two examples. The active box with 2 above and 3 to the left, so we swap the active box with 3. the active box with 4 above and 3 to the left, we swap the active box with 4. And again, the point is that outcome is locally standard. In the picture which we get, the outcome is standard, and the active node moves upwards or to the left. Now we can define the backward slide. So the input for the slide is a skew generalized Young tableau with different entries of shape lambda modulo mu and a fixed insertable node for lambda. And the algorithm goes as follows. We declare our fixed insertable node of lambda active. And while the active node is not an insertable node of mu, we perform an elementary backward move for this node. As an output, we will get a new skewed generalized Young tableau of subshape lambda prime modulo mu prime, where lambda prime is obtained from lambda by inserting the originally fixed insertable node, and mu prime is obtained from mu by inserting the active node at which the algorithm terminated. Here is an example. So assume that we have as an input the following diagram of the shape 5, 4, 3 modulo 2, 1, which has 2, 3, 4 in the first row, 1, 5, 6 in the second row, and 7, 8, 9 in the third row. And we declare active the insertable node for this diagram in the second row. So it's second row and position 5. So let us now do the algorithm. For this active node, we have 4 above and 6 to the left. So 6 is greater, so we swap the active node with 6. For this new active node, we have 3 above it and 5 to the left. So 5 is greater, so we swap this active node with 5. For this new active node, we have 2 above and 1 on the left. 2 is greater, so we swap this active node with 2, and we get our active node in an insertable position for mu. So the algorithm terminates here, and as an outcome, we have a skew diagram of the shape 5, 5, 3 minus 3, 1, which has 3, 4 in the first row, 1, 2, 5, 6 in the second, and 7, 8, 9 in the third. And one can easily observe that this is exactly the inverse of our previous example of the forward slide, and directly from the definition, one derives the property that the backward slide and the forward slides are inverses of each other if we appropriately choose the starting acting nodes. So now we can describe this general notion of jeu de taquin. Definition: we call two skew tableaux equivalent, provided that there is a sequence of forward and backward slides which transforms one of these tableaux into another. Here is a theorem which is due to Schutzenberger. It says that each equivalence class of skew tableaux contains a unique tableau of partition shape. And for the proof of this theorem, I refer to theorem 377 in Sagan's book. That's quite a lengthy argument. And let us introduce the notation. For a skew tableau P, let us denote by J of P this unique partition-shaped representative of the equivalence class of P. And the terminology: any sequence of slides transforming one skew tableau into another skew tableau is called jeu de taquin. So the origin of this is the following. So the theorem itself comes from the paper La correspondance de Robinson by Schutzenberger from 1977. And the formal translation of the name jeu de taquin is the teasing game, but it is also the French name for the 15 puzzle. So the 15 puzzle consists of the 4x4 box with 15 bricks in this box marked by numbers, which are normally organized 1, 2, 3, 4, 5, 6, 7, and so on, left to right, top to bottom. But then the point of the puzzle is that one takes away the bricks of 14 and 15 and puts them in the wrong order, and then the point of the puzzle is to transform this placing of the bricks into this placing by sliding bricks using this empty box for the possibility to slide the bricks into. And the general hint is that this is not possible, and one can prove mathematically that you cannot transform this disposition of bricks into this disposition of bricks using slides. So let us go on and define the delta operator. Let X be a standard generalized Young tableau of some partition shape, say lambda. So we define the delta of X as follows. So delta of X is a tableau which is obtained via a forward slide applied to X with the top left box removed and declared active. So for example, let X be the following tableau of shape 3, 3, 2. It has 1, 3, 5, 2, 4, 8, and 6, 7. So here's how we compute delta of X. So we remove 1 and declare this box active. So it has 3 to the right and 2 below. 2 is smaller, so we swap 2 and the active box. The new active box has 4 to the right and 6 below. 4 is smaller, so we replace the active box and 4. And the new active box has 7 below and 8 to the right, so 7 is smaller. So we replace the active box with 7, and now the active box is removable. So delta of X is the following tableau of shape 3, 3, 1, which has 2, 3, 5 in the first row, 4, 7, 8 in the second one, and 6 in the third row. So we denote by delta 0 of X the original tableau X, and by delta to the power I of X the tableau delta applied to delta to the power I minus 1 of X, if I is greater than 1. One of the main properties of the delta operator is that if X is a standard generalized Young tableau of some partition shape, then so is delta of X. To prove this, it is enough to check that elementary move forward preserves standardness locally. So each elementary move forward is a local move, so it only changes something locally, and we only need to keep track what is going on there locally. So this move works as follows. So we have an active box surrounded by other boxes, and then it is swapped with either box to the right or the box below. Let's consider the situation when the active box is swapped with the box to the right. So since the starting situation was standard, we have that A is smaller than B, smaller than C, smaller than M, smaller than Z, and A is smaller than K, K is smaller than X, X is smaller than Y, and Y is smaller than Z. And since the active box is swapped with M, it follows that M is by definition smaller than Y. But then if we look at all these inequalities and in the resulting picture, we see that the resulting picture is indeed standard. And the move when we swap the active box with the box below is similar, or actually can be dealt by using the symmetry of the picture with respect to the reflection with respect to the main diagonal. Now we can define the notion of evacuation. Let X be a standard generalized Young tableau of some partition shape. Let's say the shape is the partition lambda of N. Define the tableau X0 as X, and we define Y0 as a Young diagram of lambda with empty boxes. Now for each I from 1 to n, we define xi as delta of xi minus 1. In other words, it's delta to the power I of x. And we also define yi by filling in the box. And this box should be the box which is obtained if you take the shape of xi minus 1 and subtract the shape of xi. So this gives us a unique box. It's a removable box for xi minus 1. And we fill this box in the tableau yi minus 1 by the number n plus 1 minus I. And the resulting tableau yn is called the evacuation tableau for x. and is denoted by evacuation of x. Here is an example. So let us compute the evacuation tableau for the following Young diagram of shape 3, 3, 1. So it has 1, 3, 5 in the first row, 2, 6, 7 in the second row, and 4 in the third row. So we start with x0 being x and y0 being the empty Young diagram of shape 3, 3, 1. Next, let us compute x1, which is delta of x0. So we start with x. We remove 1 and declare this node active. It has 3 on the right and 2 below. 2 is smaller, so we swap 2 and the active box. This has 6 on the right and 4 below, so 4 is smaller, so we swap 4 and the active box. And now the active box is removable. So this means that x1 has shape 3, 3 and 2, 3, 5 in the first row and 4, 6, 7 in the second row. And y1, so in y1 we fill in our active removable box where the algorithm terminated with the maximal possible number 7. Okay, next we compute x2, which is delta of x1. We start with x1, remove the top left box, declare it active. It has 3 on the right and 4 below. So 3 is smaller, so we swap the active box and 3. The new active box has 5 on the right and 6 below, so we swap it with 5, which is smaller. And the new box only has 7 below, so we swap it with 7. And now the active box is removable. So this means that x2 has shape 3, 2 with 3, 5, 7 in the first row and 4, 6 in the second row. And in y2, we fill in with 6 the active box in which our algorithm terminated. This was the box 3 in the second row. Next, we compute x3. This is a delta of x2. So we start with x2, remove the top left box, declare it active. So 4 is below, 5 is on the right, 4 is smaller. So we swap the active box and 4. This one only has 6 on the right, so we swap it with 6, and now the active box is removable. This means that x3 has shape 3, 1, with 4, 5, 7 in the first row and 6 in the second row, and our terminating active box was in row 2, position 2, and in y3 we fill this box with 5. Next we compute x4, this is delta x3. We start from x3, remove the top left box. This is active, it has 5 on the right, 6 below. We swap it with 5, it only has 7 on the right, so we swap it with 7, and now it is removable. So x4 is 5, 7, and 6, and in y4 we put 4 into row 1, position 3. Now we compute x5, this is delta of x4. We start with x4, remove the top left box. This one has 7 on the right and 6 below, so we swap it with 6, and this is removable. So x5 is just 6, 7, one row, and in 1, 5, in row 2, position 1, we put 3. So next we compute x6, which is delta of x5. We start with x5, remove the top left box. So this only has 7 on the right, so we swap them and the outcome is removable. So x6 is just 7 and y6 has 2 in row 1, position 2. And the last step is trivial. So x7 will be empty when we remove the 7, and we just place 1 in position 1, 1. So the evaluation of x is the following diagram of shape 3, 3, 1. It has 1, 2, 4 in the first row, 3, 5, 6 in the second, and 7 in the third row. Now we can formulate the main theorem. For sigma in Sn, recall that we denote the Robinson-Schensted correspondent of sigma by P of sigma, Q of sigma. So this is a pair of standard Young tableaus of the same shape. The shape is some partition lambda of n. Recall that for a permutation sigma which sends 1 to a1, 2 to a2, and so on, we have the reversed permutation sigma r, which sends 1 to an, 2 to an minus 1, and so on. And we know that the insertion tableau for sigma r is the transpose of the insertion tableau for sigma. Theorem by Schutzenberger: the recording tableau for sigma r is the transpose of the evacuation tableau for the recording tableau of sigma. Here is the idea of the proof. In order to prove the theorem, one needs to do a lot of work. So first of all, one needs to define the delta operator generally for skew tableaux by removing the smallest element of the skew tableau. Then one can show that the delta operator commutes with the unique Jedutakin representative of the equivalence class of skew tableaux. Next, let us denote by sigma overline the function which is obtained from sigma by removing 1 and the value a1. So the key point is to show that the recording tableau for sigma overlined is exactly the delta of the recording tableau of sigma. Then, by induction on n, this observation implies that in order to prove the main theorem, it is enough to show that the box n occupies the same position in the recording tableau for sigma r and in the transpose of the evacuation tableau for q of sigma. And again, using some computation, this reduces to the same observation that q of sigma bar is equal to delta of q of sigma. And for the full proof, I refer to theorem 394 in Sagan's book. Here is an easy example. Consider sigma to be the permutation of S4, which sends 1 to 3, 2 to 4, 3 to 1, and 4 to 2. Then sigma r sends 1 to 2, 2 to 1, 3 to 4, and 4 to 3. So let us compute the Robinson-Schensted correspondent of sigma. So we start with a pair of empty tableaux, then we insert 3 to get 3 and 1. Then we insert 4, 4 is greater than 3, so we get 3, 4, and 1, 2. Then we insert 1, 1 bumps 3 into the second row, so we get 1, 4, and 3, 1, 2, and 3. And finally we insert 2, 2 bumps 4 into the second row, so we get the insertion tableau 1, 2, and 3, 4, and the recording tableau 1, 2, and 3, 4, both of shape 2, 2. Next, let us compute the Robinson-Schensted of sigma r. So we start with the empty tableaux. First we insert 2 to get 2 and 1. Next we insert 1, which bumps 2, so we get 1 and 2 as the insertion tableau and 1 and 2 as the recording tableau. Next we insert 4, which goes into the first row, so we get 1, 4, and 2 as the insertion tableau and 1, 3, and 2 as the recording tableau. And finally, we insert 3, which bumps 4 into the second row. So we have 1, 3, and 2, 4 as the insertion tableau, and 1, 3, and 2, 4 as the recording tableau, both of shape 2, 2. So now let us compute the evacuation tableau for q of sigma. So q of sigma is 1, 2, and 3, 4. So we remove the top left corner. It's active. It has 2 on the right and 3 below. So we swap it with 2. The new one has only 4 below, so we swap it with 4, and now it's removable. So it gives us the empty Young diagram of shape 2, 2, with the box 4 occupying the position 2, 2. Next, we start with 2, 4, and 3, so this is the outcome of the previous procedure. We remove the top left box. This is active. It has 3 below and 4 on the right. 3 is smaller, so we swap it with 3, and now it is removable in position to 1. So in our empty diagram originally, we also fill 3 in position to 1, and this is the outcome. So we continue with 3, 4 in the first line. We remove 3, and now we only can swap the empty box with 4. So this gives us that we should fill with 2 the box in position to 1 in our Y sequence. And finally, we have 4, which we remove, and so we need to fill 1 in our position 1, 1. So the evacuation tableau for Q of sigma is 1, 2, and 3, 4. And this is exactly the transpose of the Q for sigma R. So this verifies our main theorem in this example. So let us finish with some problems and questions. Question 1. Prove with all details that the backward and the forward slides are each other inverses. Of course, when the active boxes are specified appropriately. Question 2. Compute the evacuation tableau for the following Young diagram of shape 331. It has 1, 3, 4 in the first row, 2, 5, 7 in the second row, and 6 in the third row. Question 3. Find a tableau X whose evacuation tableau is 1, 2, 3, 4, 6, 7, and 5. Question 4. Find all tableaus X of shape 3 to 1 which coincide with their evacuation tableaus. And question 5. Find all tableaus X of shape 3 to 1 which coincide with the transpose of their evacuation tableaus. Thank you very much, and see you next time.